Hi Year 9, welcome to my lesson on covalent bonding. So in our last lesson we were looking at ionic bonding, which is when we had a bond between a metal and a non-metal. The bonding type is called ionic. Today we're going to consider what would happen if we have a combination of non-metals. So if we think back to when we had ionic bonding, we had metals in groups 1 to 3, which lost electrons, either 1, 2 or possibly even 3 electrons, and then we had other atoms in groups 5, 6 and 7 which were looking to gain electrons, all to get that full outer shell. But if you remember, we never discussed group 4, because for group 4 it would be far too difficult for that to lose or gain a total of 4 electrons. So the question is, what happens when we try and involve elements like group 4? So to help you with this, I'm going to pose you another analogy. So the analogy is this: you've not long made your option choices, and some of you have opted to do art and others haven't. So here's my analogy for you. Let's say those of you who have chosen to do art are going to be set a project, and that project involves you requiring 8 pencil crayons to complete the project effectively, but you only have 4 pencil crayons in your pencil case. And for those of you who are who have chosen not to do art, you have a much simpler art project to complete, and your art project will require you to use 2 pencil crayons to complete the project, but you only have 1 pencil crayon in your pencil case. So the question that I'm posing to you is, how will you as artists and non-artists work together to ensure that you are all able to complete your project? Have a think, press pause and play when you think you've got the answer. So the expected answer is that you might choose to share your pencil crayons in order that you can get what you need to complete the project. And that is exactly what our non-metal elements do in order to bind together. They share electrons. Now, when they share electrons, they form what is called a covalent bond. The clue is in the word covalent, just like at the beginning of the word cooperate. So they are sharing. And when they share electrons, it's always a fair sharing. So one element would share an electron in order to get an electron shared from another element that they are joining with. So let's have a think about an example, and the example we're going to look at is methane. Do you know what the formula for methane is? If you do, it can help you to govern what you've actually got to draw. So the formula for methane is CH4. And what that is effectively telling you is that you are going to have to draw 1 carbon and 4 hydrogens to complete the diagram, the dot and cross diagram. So we're going to be using dots and crosses for the electrons from carbon and hydrogen. You're going to have to draw 1 carbon and 4 hydrogens in order to be able to complete the molecule for methane. So let's start by thinking about carbon. Now, for this example and for all the examples that I'm going to do on the board, I am going to just show you the outer shell electrons, because it is only those outer shell electrons that are involved in the bonding. If in an exam you had to draw all the other electrons as well, you would just fill those up on the shells underneath the outer shell, the inner shells, however many that might be. You just fill them up and then focus on the sharing for the outer shell electrons. So let's think. Carbon is our main element here because there's just one of it. So what I'm going to draw is carbon. Now, if you've got a periodic table handy, you can look up where carbon is in the periodic table. Carbon is, of course, in group 4, and that means it has 4 electrons in its outer shell. If it has 4 electrons, how many is it going to have to share in order to get back the 4 electrons that it needs to take the total up to 8? The answer is it's going to need to share all 4 electrons, because remember we said it's only ever going to be fair sharing. So carbon has 4 electrons, so I'm going to put those round as 4 crosses. Now it's joining with hydrogen, so hydrogen is a bit like our non-artist within our analogy, and hydrogen has just 1 electron in its outer shell, but of course it wants to have 2. So in order to get that second electron, it has to share its only electron in order to get one back from carbon. So carbon therefore has to share 1 electron with each hydrogen. So here's a hydrogen, here's its 1 electron on the shell there, and it's sharing one of carbon's electrons. I'll show you in a minute an alternative for how you can draw that that's perfectly acceptable. So there, hydrogen's electron is our dot, sharing with our cross from carbon, and of course the formula being CH4. That's because carbon has to share each of its electrons with a hydrogen, thus getting 4 more. So it shares all 4 of its electrons in order to get the 4 extra electrons to take the total up to 8 and have a full shell. Now once you've drawn what you think you need to draw, you should always go about checking. So for any hydrogens involved in molecules, you need to check that you've got 2 and only 2. One thing that is a common mistake for students to do is actually draw an electron twice and end up sharing their electron for hydrogen, and for whatever reason ending up trying to put their electron out here as well. Now if you do that, of course, when you check round you'd see that you've got 3, which is too many. You should always have pairs of electrons in the sharing, never odd numbers, and it's going to be a fair sharing, so you're going to have 1 electron from each for each covalent bond that you have. Now in chemistry you often see diagrams where you have lines drawn for covalent bonds. So you might have seen previously a diagram of methane shown like that, with carbon surrounded by 4 hydrogens. Each of these lines represents a single covalent bond, and it represents a shared pair of electrons. So what I want to do is to think about the fact that there are going to be a very limited number of possibilities for how different elements can arrange their electrons and share electrons with other atoms depending on from which group they've come from in the periodic table. Let me use this as a further example. So here I have methane, CH4. I can, with doing very little to this diagram, change this into something called silane. And all I need to do is change my label from a carbon to a silicon. Silicon is also in group 4, and when silicon bonds with hydrogen, it has to do exactly the same as carbon. It has to share all 4 of its electrons in order to get 4 back in return from 4 separate hydrogen atoms. Each hydrogen atom has to share its only electron with the silicon in order to get 1 back in return. And you're checking round, you've got 2 for every hydrogen, and your other check that we need to do is make sure any other element has a total of 8. So here you can see silicon has 2, 4, 6 and 8. So a full outer shell for my silane. Now if I take that back to carbon, I'm going to show you how we can change that again to make even more examples without changing that sharing of electrons. Now if you think about it, in the periodic table there are other elements that only require one more electron. Where are they? That's right, they're in group 7. So group 7 has something in common with our hydrogen here. It only needs one more to fill up the outer shell, which means it needs to share one in order to get one back in return. And what that means is I can turn this very easily into other molecules. So I'm going to label that as a chlorine, Cl, and all I need to do, so the sharing stays the same, but to turn that effectively into a chlorine atom, of course chlorine has got 7 of its own outer shell electrons because it's in group 7. And that's because 6 of the electrons are not involved in the bonding. 1 electron is, and that's the 1 electron that it shares with the carbon in this case to pick up that 8th. So when we're counting round, we check that that has got 8. Now the other thing that you have to watch out for as a student is that when you are drawing your diagrams, if you've got elements that don't involve all the electrons in the sharing, that you don't forget to draw those in, and that's where your checking mechanism comes in very handy. So once you think you've finished, checking round for 2s for hydrogen or 8s for any other elements. In this case carbon has 8, chlorine has 8. So that is the molecule CH3Cl. The sharing pattern has not changed for any of the molecules I've talked about so far, and that would continue. I could change any of those to chlorines or any other group 7 element, and all I would need to do is make sure that I'm putting in what we call those non-bonding electrons. So chlorine has 7 of its own, that's 7 dots, and it's getting the cross by sharing with carbon. And I could change any of those and change it into, for example, I changed these others as well, I change it into something called tetrachloromethane, which is CCl4. Now, I'm just going to talk to you about how else you can draw the pattern. You'll see I've put them on the actual shell lines, but as long as it is clear sharing, if we've got the 2 overlapping shells here, you can put those electrons in that shared space there. That's fine. Just be careful, particularly with crosses, that they don't get hidden on the lines there, or that you don't put any other electrons from around too close to that area and unable to be seen. Also make sure that you draw your electrons nice and clearly using a nice sharp pencil. And when you're drawing your shells, do be careful in your examples that when you draw around your circle, you don't have this bit that looks like a cross because you've drawn your circle so quickly, ends up looking like an electron. So clarity is really important, checking is really important, and being careful that you consider 2 things. Have you only drawn the number of electrons that that atom has of its own, so that many dots or that many crosses, and have you, once you've finished, got a total of 2 or 8? Because it's very easy to just try and make it fit by adding in a couple of extra crosses and actually making it an incomplete, an incorrect example. So what I'd like you to do now is to pause the video and to complete the examples of covalent bonding that I have set you on the sheet. So hopefully you've all had a go at the covalent examples on the sheet. If you haven't quite finished, then what I suggest you do, or if you're unsure about some of your answers, is that you watch through and check the first few. If you find you've made mistakes, perhaps pause the video again, have another look through and try and correct some, and then play the video again to go through the remaining examples when you think you're happy with what you've got. So, the first one was hydrogen, H2. That has, each hydrogen has one electron in its outer shell. So the question you should be saying to yourself is, how many does it have in its outer shell? 1. How many does it need in order to get a full shell? The answer is that hydrogen will need another 1. So in order to do that, it has to share its only electron to get 1 back in return. And so it shares it with another hydrogen atom. So you have your shared pair. Each hydrogen has 1 electron, so 1 cross, 1 dot, but overall I now have a shared pair. That overall each hydrogen now has 2. If I wanted to draw how that is joined as a molecule, I would show that with a single covalent bond between my 2 hydrogens. Okay, so that is hydrogen. So we're going to move on. Our next example on the sheet, should you not have a sheet, the next example to try is chlorine, which is Cl2. So chlorine has how many electrons in its outer shell? The answer, of course, is 7. So chlorine has 7 electrons in its outer shell, and therefore it has to get 1 more. So it has to share 1 to get 1 in return. So here's my electron it's going to share, and it's going to share it with another chlorine atom, which also has 7 electrons of its own, and again has to share 1 to get 1 back in return. And so now we count round. This chlorine on the left has now a total of 8, 7 of electrons of its own, 1 that it shared from the other chlorine atom, and the same on the right. 7 dots, 7 of its own, and then 1 shared to make a total of 8. Okay, our next example that you should have attempted was actually methane. So just to recap, on the board to double check you've not made a mistake, remember you should have your carbon in the centre surrounded by 4 hydrogen atoms. Each hydrogen atom has 1 electron of its own, which it has to share to get 1 back in return from each carbon. And of course carbon has 4 electrons, all of which have to be shared. So I have got 4 crosses for the carbon, 1 dot for each hydrogen, but we've now got a shared pair for each. No electrons, please check that you have no electrons in any of the shells that are not being shared. Okay, that's a common mistake. Okay, our next one was a little bit trickier, and we'll judge whether or not you've understood this. So this is water, which hopefully you know is H2O. So H2O gives you a clue that you're going to have to draw 1 oxygen and 2 hydrogens. So oxygen, let's start with that. Oxygen has 6 electrons of its own. So I'm going to give oxygen 6 dots. Okay, now if it has 6, how many does it need to take it to be full? That's right, you need to get 2 more, or have a share of 2 more. So in order to get 2, it has to share 2. But what it's sharing with is hydrogen, and each hydrogen only has 1 electron and only wants 1 back in return, and that's why it needs to share with 2 hydrogen atoms. So this electron can be shared with a hydrogen, and that hydrogen gives one back in return, so you have a shared pair there. And this electron here also can share with a hydrogen, getting one back in return. This of course is your oxygen. So oxygen, 6 dots, or crosses is fine if you chose crosses, and hydrogen, 1 cross in this case for each. Check. Oxygen now has a total of 8, hydrogens have a total of 2. So you have HOH. Don't worry if you haven't drawn it with this angle, that doesn't matter at this stage. So that's water. Now comes the trickiest of all the ones that I asked you to do, and no doubt some of you will have got stuck here. So before I go through carbon dioxide, I'm just going to talk to you about oxygen as a molecule, and it might help you to complete carbon dioxide. You can go back and have another check before going through the rest of the video to watch for the answer. So oxygen. Oxygen of course exists as what we call a diatomic molecule. It goes round in a pair, O2, O with a subscript 2 next to it. That is because it has to share electrons in order to have a full outer shell. This is the whole reason that molecules like oxygen, hydrogen, chlorine, nitrogen, they all go around in pairs because of the way they covalently bind together. So oxygen has 6 electrons of its own in the outer shell. And as we stated, it needs to get 2 more, get a share of 2 more. In order to do that, how many does it have to share? That's right, it has to share 2 to get 2 back in return. And so the difference with this is that we have more than one pair of electrons sharing between our 2 atoms. So if I draw my oxygens, a nice big overlap. So each oxygen has 6 electrons of its own, and remember it has to share 2 of them. So I need to have 2 shared pairs in that overlapping section, or on those overlapping lines. 2 have been drawn, so we take it up to the 6. So 1, 2, 3, 4, 5, 6 crosses for this one, and 1, 2, 3, 4, 5, 6 dots for the one on the right. When you count in the crosses from the one on the left, that gives a total of 8, or here also a total of 8. So in the middle there we have 2 shared pairs of electrons. So if we were drawing that out with our lines, you put 2 parallel lines between the oxygens, and that is what we refer to as a double covalent bond. So each oxygen is sharing 2 electrons, and in return the other oxygen atom is sharing 2 electrons as well. So we've got 2 shared pairs, and therefore it's referred to as a double covalent bond. So let's now look to carbon dioxide. CO2. So let's start with our carbon. Carbon is in group 4. That means it has 4 electrons in the outer shell, and it has to therefore share 4 electrons, all 4 electrons, in order to get a share of 4 more. Here we know it's only sharing it with 2 things, 2 oxygens. So we know we're going to have 2 oxygens like that. Now hopefully it will make sense to you to think that if it's going to have to share all 4 electrons, it's going to do that 2 with each of those oxygens. And of course every time we share an electron, we're going to get 1 back in return. So I'm going to put 2 dots in there. Notice I am putting dot cross so that I can see those pairs of electrons ideally. Looking at the oxygens then, I've already drawn 2 of those electrons, so we need to take that up to oxygen's outer shell total of 6. So 1, 2, 3, 4, 5, 6, and the same on the other side. 1, 2, 3, 4, 5, 6. Now we have a double check. We have a total of 8 here, 4 non-bonding electrons and 4 that are involved in the bonding, and the same for the other side. 4 bonding electrons, 4 non-bonding electrons, totaling 8. And our carbon, of course, has 8, 4 and 4. Do check, please, that you have remembered to include the non-bonding electrons for the oxygen, and also double check that you have not put any electrons in this space around here. For some reason, students often repeat electrons. They're putting them in the shared section and then repeating them in the non-shared section, and that's why it's important to check that you've only got 8 at the end of your diagram completion. Just before we move on, if you wanted to draw that, that would be C and double bonded each side to an oxygen. So we have CO2. Okay, so we're going to move on to our next example. I'm just going to change my pen to make sure you can see nice and clearly. My next example is ammonia. Now, ammonia has the formula NH3. Remember not to get confused with ammonium, which is an ion and is formed within a compound. It has to be joined to something else. Ammonia exists as a molecule on its own and has the formula NH3. So let's consider our main atom, which is our nitrogen. What group is nitrogen in? That's right, it's in group 5, and that means that it has 5 electrons in the outer shell. 1, 2, 3, 4, 5. If it has 5 electrons in the outer shell, how many more does it need? That's right, it needs 3 more, and to do that, it has to share 3 electrons to get 3 back in return. And it's sharing with hydrogen. And remember, with all our examples, every time we use hydrogen, hydrogen has 1 and therefore has to share its only 1 electron to get 1 back in return. And that is why it needs to share with 3 separate hydrogen atoms. Shared pair there, a shared pair there, and a shared pair there. So 3 hydrogens, each with a shared pair, and then nitrogen, because it has 5 of its own, 1, 2, 3 involved in bonding, 4, 5. But now we have a total of 8. 2, 4, 6, 8. Hydrogen has 2. Make sure you've not got any electrons in this outer bit here, otherwise you've duplicated some of them. Make sure you do have, however, this, what we might refer to as a lone pair of non-bonding electrons. They don't have to be shown as a pair, you might have separated them out, and that's fine, as long as you've got a total of 8, 2 that aren't involved in sharing, and 3 that are, which allows it to pick up another 3 and total 8. Okay, on to one of our final examples. A nice simple one, hopefully. And that is hydrogen chloride, HCl. So hydrogen and chlorine. Hydrogen has 1 electron, which it has to share to get 1 back from chlorine. Chlorine, of course, in group 7, 1, 2, 3, 4, 5, 6, 7. Total 8, total 2, you're done. HCl. Now our final one is an interesting one. Our final one was H2S. Now, if you look further up your sheet, hopefully you will find a similarity with one of the ones you've already done. And that is exactly the same, apart from the labelling on the atoms, as that of water. Because H2O and H2S, and of course O and S, are both in the same group. They're both in group 6. And that means that the sharing pattern is exactly the same. So we have our S in this case, which should have, just like in water, our 4 non-bonding electrons, or 2 non-bonding pairs you might say, and then our 2 shared pairs for hydrogen, and that is H2S, hydrogen sulfide. Hopefully you've understood that. Take a look on Insight for those of you who I teach, and check out some additional work on there. Thank you very much for listening.